C.V. Kamesh, Professor of Mechanical Engineering, Aditya Engineering College. In this lecture, we would like to know how the velocity will be calculated at different points in a mechanism by relative velocity method. So initially we would like to know what is the velocity of a point on a link, then we will progress to how to find the velocity of different points on a link outside of the link or in between the link. So initially we will take one link AB. So this is some irregular body is taken. On this body, why we are taking the body means it is deemed to be a rigid body. Rigid body means whatever the force of application on this by some external means F1, F2, F3 some forces are acting or by means of the rotation continuously like this, the physical parameters between any 2 points, that means the length between A, B. Suppose I am taking A here, B here, the distance between the points A, B should not change. So always in this case we are taking all the bodies are rigid bodies. So this rigid body is moving in a direction omega like this. Why the irregular shape is taken? Because the rigid body can have any of the shape either regular or irregular, but the body is moving in a definite direction with angular velocity omega. So it may be rotating like this or it may be rotating like this. So here there may be the center of rotation like this, A is the center of rotation, or B can be taken as the center of rotation, or another point C can be taken as center of rotation. It does not mean that the center of rotation need to be at the center of gravity of the rigid body. We can have any point, any eccentric point or interior point we can take the center of rotation. Now here the rotational velocities of A will be VA and velocity B will be VB. So how these two are represented in ordinary case, and we will take the in between point C and another point D outside the link. So these velocities, the A velocity VA is known to us. Initially velocity of is given as in horizontal direction. That means point A may be a part of a slider. That means it is moving like this. Then the velocity of A will be horizontal direction VA. Now given velocity of A, magnitude and direction as an input parameters and the length parameters are given as another input, then the VB direction is given to us. But what is the magnitude of VB? VB direction only, no magnitude is given. So we need to identify what is the magnitude of VB. So it is to be known, and moreover, what is the velocity of B with respect to the A? VBA. Always the representation is velocity of the primary element is B, and second is the reference element should be written here A. Suppose there are some other links A, B, C, D like this. I want to find velocity of C with respect to A, then I need to write VCA. If the D, velocity of D with respect to C, VDC, velocity of D with respect to B, VDB, or velocity of B with respect to the D, VBD. Like this, we are having same notation for any 2 points, relative velocity of some primary element, reference to second. So how to find the velocity of B with respect to the A? So the first thing we need to do is we will take some sufficient scaling for VA. This VA is represented from a standard point or fixed point O. So initially we will take OA as the standard point and OA. 2 points are taken. This is the representation of VA. After that, initially we don't mind anything about the VB. First thing we need to know the relative velocity of another point with reference to starting point. That means first we need to identify where is VBA. Earlier we know in the motion of the link, the velocity at any point on the link when the link is in the rotational area, it is always perpendicular to the length of the link or the rotation. That means the body is rotating like this, it is perpendicular to the radius at any point. So here it is, AB is the radius. So to the radius it will be perpendicular like this. So this is the direction of the velocity VBA. So velocity of B with respect to the A, it is to be considered as in the chart AB. So starting with the A, in the direction of velocity BA, we need to draw a line. So A, so taken as the mini drafter or set squares, we need to draw a parallel line from A parallel to this velocity inclination. So from this we need to draw a parallel line like this. This is representing VBA. That means VA is represented here and VBA is represented here. Now VB direction is given to us. VB direction is given to us. Then VB means basically it is VBO. Velocity of B with reference to standard point O. So from O I need to get OB. So AB. So B is simply not known to us. Again I need to draw OB in the direction parallel to given direction OB. So I am targeting it, try to draw OB in this direction. So take this direction and draw a line. So this is in the direction VBO or VB. Both can be taken. So this is the line where B is present and this is also the same line where B is present. That means we are trying to get the locus of B through AB, locus of B through OB. So the intersection of these we will get B. The same thing is represented here. This is OA and this is VBA and this is VB. When I am taking the scaling of the VA onto the chart, same scaling we need to apply to get the magnitude of B. So OB will be magnitude of this chart length OB, whatever the scaling. It may be 1 meters per second is equal to 1 mm or 1 centimeter or 10 centimeters. Based on the scaling, the same scaling of OA is applied to the OB, then magnitude of VB can be known to us. Now the case is how to identify the intermediate point velocities. So these intermediate point C is taken. Just like in the earlier case we discussed about where to locate the intermediate point on the chart diagram. So this AB, this is small a, small b. That means velocity of B with respect to A is already known, its direction is known. And more interesting point is, if any link is there like this A, B, velocity of B or C or D or E or any other thing, all are in parallel directions. So this will be VB, this will be VC, this will be VD, this will be VE. all are parallel. All are parallel and in the same direction, because this is rotating like this. When this is rotating in this direction, this point rotation will be in one circle, this point rotation will be in another circle. Let us take that this is the link, this is rotating like this, some link is there, this is O, this is A, this is B, this is C, like this. So, this is the original circle, whatever we are seeing with the tip moving like this. But inside we are having another point, B is there, C is there. So, this is having one circle, this is having another circle. So, each and every circle will have a certain link length that is to be applied in the equation V is equal to R omega. Omega is constant and R means the particular length OA or OB or OA or OC, anything. So, all the required lengths of intermediate points are parallel to each other and they are getting some location exactly as the whatever the composition they are having, and they link the same thing on the velocity diagram, because omega is constant. These velocity diagram and the link lengths, they are 100% proportionate. So, this proportionality is coming onto the diagram like this. So, we need to identify the point C on AB. So, identify the point C on the length AB. How to identify? So, AC by AB should be equal to AC by total AB should be equal to this AC original length divided by original link length AB. So, AC by AB. If we know already the parameters AB calculation, then this can be fed like this into AB like this. AC length will be given in the problem statement, AB length will be given in the problem statement, and a small AB, this is the velocity of B with respect to the A. If this is scaled and calculated, then we can substitute and we can find analytically like this. Otherwise, we need to use some graphical method, same thing like this. This is A, B. From this we need to draw actual AB onto the same diagram with any angle. This angle need not be some theta or delta or something, any angle we can take. So, this is regarded as capital A, this is regarded as capital B, in between I am taking C. So, join these two and draw a parallel line, then I will get C. This is the most easiest method, but if we are able to draw AB, then only it is actual, otherwise we need to calculate analytically and make it approximated. So, after identifying point C, then the velocity of C with respect to A. So, this is in this direction. Velocity of C with respect to A or velocity of C with respect to O can be known by joining with that particular point. So, velocity of C with respect to A, that means V CA is equal to AC. Suppose the velocity of C with respect to the O, I need to calculate. Join with O, simply join with O. So, it is equal to OC. Like this, whatever the relative velocity of a particular point with reference to any secondary point we need to identify, simply join with that in the velocity diagram, then measure this length parameter, make it scaled and identify what is the value of VCA, what is the value of VCO. From the chart, it is very easy to calculate. Now, next thing is, when a point is on the link, it is okay. So we are able to take the proportionality calculations and we are identifying on the diagram C is okay. But now we are having some offset point somewhere at some distance. So it is having some angle with AB with theta and from BA it is some phi. So these same angles cannot be fed here. There is an easy method how to identify the point D in the velocity diagram. So you join with the starting points of the links A to D and B to D. So when we consider the A, B, D as a single entity, then the body is moving in this direction and the line AD. So D is identified as a point on a link AD. D is again identified as a point on another link BD. That means AB is one link, BD is another link and DA is another link. When we call the entity as a separate link, automatically the velocity of the link AD, the velocity of link BD, they will come into the picture. So once velocity of D with respect to the B and velocity of D with respect to the A are considered, automatically velocity of DA has to be perpendicular to the link AD. Again, velocity of D with respect to the B is considered, velocity of D with respect to the B has to be perpendicular to the link BD. So the similar fashion we are identifying this AD. So velocity of D with respect to A is to be identified, velocity of D with respect to B, this is to be identified. That means AD is to be drawn and BD is to be drawn. When AD is to be drawn and BD is to be drawn, automatically we will get the intersection point will become small d, right? So what is the principal thing now? AD direction is to be known to us and BD direction is to be known to us. So if you draw the two lines AD in one direction, BD in another direction, they will have an intersection, then we will get the point D very clearly. So AD direction, what is the direction of AD? It is perpendicular to link AD. That means this is AD. This is the link AD. Perpendicular to this, you draw AD locus line. So with the mini drafter or set squares, you take the direction like this, and from A, we need to draw a line like this. So for this line, there is a perpendicular line from this like this. So these two are perpendicular. Basically, it need not be in the vertical direction. Once we are drawing AD, this means we need to draw a continuous line. Actually, this can be extended like this. This we need to represent as locus of D. It is giving only the direction and it is the locus line only. It may be vertical, it may be downside, we don't know in the initial case, but represent as locus of D. Now, BD. What is the direction of BD? It is perpendicular to the link BD. Now we will take BD into consideration. This is BD. So to this perpendicular from B. So take this is the line and perpendicular from the B point, we need to draw another line. So here also extend towards left and right, locus of D. Here also I am writing locus of D. Now there are the two locus, this is the locus of D and this is the locus of D. So there is an intersection. Now this will become point D. After identifying this point, what we need to get? Now this point D is located on the diagram. Now I can get velocity of all the velocities. Velocity of D is identified. D is already joined with A. After getting the intersection, AD is known to you and BD is known to you. So velocity of D with respect to the A, it will be in the upper direction VDA. Velocity of D with respect to the B, in this direction it is VDB. So VDA will be known by calculating the length AD, not AB, it is AD. Now velocity of D with respect to the B is known to you by calculating the length BD and make it scaling, get the calculation. It may be some 10 meters per second and this may be 5.2 meters per second, like this we will get it. So velocity of D A, velocity of D with respect to the B known to you. Now if we want to get the velocity of D with respect to originated point or starting point or fixed point O, then join with O, then it will be called velocity of D with respect to O, or because this is the fixed point, we can remove the point O, we represent as VD, right. So this can be known. If we want to get the velocity of D with respect to the C, then CD can be joined, then we call it as velocity of D with respect to C. Whatever the velocity of a particular point with reference to any other point, if we want to know, simply join them and get the direction. And we need not have any ambiguity or representing the arrow mark. These arrow marks are representing by means of the velocity of the head point to the tail point. So here I am representing to the rightward direction. What is this now? This is the head point D. This is the tail point C. Then I will call it as velocity of D with respect to C. Suppose I am making the reverse direction like this, D to C. Then I will call this as velocity of C with respect to D. So whether it is in the upper direction or the lower direction, it is completely immaterial. Only the given parameters VA or VBA or VB, all are initially used to identify where is the original point O, A, B, all these lengths. After construction of the velocity diagram, we can represent in the reversal directions. So by this, velocity of any intermediate point, velocity of any offset point at a distance outside of the link can be known very easily. Now, how to find the angular velocity of the link? So this omega is always, we know, velocity is equal to omega into r. R means the length of the link, omega into length of link. Suppose I want velocity of the link AB, then it will be length of link AB. Then very easily I need omega of AB now. Omega AB is equal to VAB divided by length AB. Here also we need not have any ambiguity. So sometimes it will be written as VBA by AB. In the vector notation, VAB and VBA, they are reverse in directions of the magnitude, minus VBA by AB. Now somebody will have some ambiguity, shall I represent with omega AB or omega BA? omega AB or omega BA. Both are equal. Because once I am making a statement, a crank is rotating with some angular velocity in direction, in anti-clockwise direction or clockwise direction, that is only the main point. If it is rotating with the 20 radians per second anti-clockwise, so the link AB, so omega AB equal to 20 or omega BA is equal to 20, both are in the anti-clockwise direction. So this VBA or VAB, it is immaterial. So we can write here only the magnitude portion of this VBA or VAB. We need not take the plus or minus. Simply the velocity component divided by the length component. So that's why the omega of AB or BA, either it is moving in this direction or if it is in the reverse direction, clockwise or anti-clockwise. So the velocity component divided by the length component. Velocity component will be known to us by the earlier velocity diagram. Whatever the AB portion we have, this is AB. Velocity of BA will be equal to the length portion AB. This is to be divided with the actual length AB. It may be given as some 100 mm. Always we need to convert into meters. Suppose on the AB, after calculation, it was 5.25 meters per second. Let it be. How to get the angular velocity? Omega equal to velocity by length component. So AB by the length AB. This is the velocity component. This is the length component. AB equal to 5.25 meters per second, 100 mm, 100 divided by 1000, because this is in meters per second, this has to be converted to meters. Then, so this will become 52.5 radians per second. Omega will always be radians per second. Like this, the angular velocity of any of the link, it can be calculated very easily by means of the velocity component divided by length component. So whatever the direction, that is in the initial case it is immaterial,